I want to talk about adding vectors in this video, and you may not have realized it, but you actually kind of intuitively already know how to do this, and I'll show you why I think that. If you read this problem, it says that you're riding near the front of a bus that's moving forward at 10 meters per second. And you find something on Instagram, you want to show your friend who's in the back of the bus. So you decide to walk back to the back of the bus to show your friend. If you're walking backward toward the back of the bus at 3 meters per second, and let's say your mom is standing outside the bus and she's watching you, to her, how fast do you appear to be moving? Okay, so if the bus is moving forward at 10 meters per second, you're moving backward at 3 meters per second. It may be intuitive to you that you would subtract 10 minus 3 and you would get 7 meters per second. And you would in fact be right, that to your mom standing outside, to some casual observer standing still, you would be moving 7 meters per second because your 3 meters per second is moving against the bus's speed. Then conversely, if you then walk back to the front of the bus at 7 meters per second, how fast do you appear to be moving? Well, the interesting thing about this is since you're going in the same direction as the bus, your speed actually adds to the bus and you end up actually going faster than the bus itself. You yourself, in relation to an observer watching outside, are moving 17 meters per second. Okay, so that's intuitive, but I want to show you how to figure that out using vector addition. I'm going to start out in one dimension, just straight lines forward and back. You gotta know that vector addition, to do that we always add vectors tail to head, or sometimes this is called tip to tail. Either way, it's the same thing. And you need to know that the resultant vector is what we call the sum of the first two vectors that we add. So we need to know these vector addition rules. These are extremely important. Extremely important. The first thing you need to know to add the components is that the head of the first component needs to be at the tail of the second. Don't worry about it if you don't understand this just yet. You will when I do the example here in a second. And you also need to know that after that, to draw the resultant has to be drawn from the tail of the first to the head of the second. Okay. Now, let's take this bus example and apply it to this. The two component velocities will be the bus's velocity and your velocity. So let's say the bus is moving to the right at 10 meters per second. That's its velocity vector. And if it's moving to the right, in the first instance, you're moving the opposite direction, so you would be moving to the left at 3 meters per second. Okay? So what's interesting about velocity vectors is this. I can take two velocity vectors. If I have a 10 meters per second vector, and your vector in this case would be 3 meters per second going to the left. Notice first of all that I drew these two to scale. 3 is shorter than the 10. You can't make these two equal size and say this one's 10 and this was 3. I can move these vectors anywhere I want to, but there's two things about a vector that I cannot change. One of those things is the length of the vector, and the other one is the direction of the vector. So as long as I don't change this direction, and as long as I don't change its length, I can move it anywhere on the whole place. And the reason why I want to do that is that I want my components to be oriented so that the head of the first is at the tail of the second. So that's what I'm going to do. Here's my first vector. Here's my second vector. Head of the first needs to be at the tail of the second. So literally I'm going to take this vector and slide it right up in here into place so that the tail of this one meets the head of this one, and it'll look just like this. Okay? So that's what I'm going to draw here underneath our notes. 3 meters per second vector goes right there. And now you can easily graphically see that if we draw the vectors this way, notice that the resultant has to go from the tail of the first to the head of the second. Well, here's the tail of the first. Here's the head of the second. The resultant goes from here to here. And it's quite easy to see at this point that to get the length of this vector, you would subtract 10 minus 3 and come up with 7 meters per second to the right. Remember that each vector has a direction. 7 meters per second to the right is what that one would be. And then the second example, the bus is still moving at 10 meters per second. Now you're moving in the same direction, to the right. So your velocity vector is now not 3 to the left, it's to the right, and yours happens to be, well, let's not make it this long, let's make it this long, 7 meters per second. Same thing, head of the first to the tail of the second. This tail needs to meet this head, so we're going to move it straight up into here. As long as we don't change the direction or the length, we're okay. So our added vectors will look like this. And now again, it's easy to see the length of what our resultant would be, because the resultant has to go from the tail of the first to the head of the second, tail of the first to the head of the second. And to get the length of that, you would do 10 plus 7, which gives you 17 meters per second. Easy to see, right? But now I want you to see that I didn't just make this stuff up. It's not just something there to kind of make your life miserable. This is actually real life stuff. And if you'll click on the link right now on the bottom right of your screen, it'll take you to a Mythbusters YouTube video that shows you a practical example of what we're talking about here.